Hi, I'm Rob, and I'm pleased to present our work on regularized meta-learning for neural architecture search. To first introduce the basis of our work, we build on top of MetaNAS, which combines gradient-based meta-learning and gradient-based neural architecture search. It does so as presented here on the left. We first, during the task learning, adapt our model to the specific task at hand using a number of these updates. We combine these to compute the meta loss, in which we update our meta model, our starting point for the task learning, updating the W meta and alpha meta. This meta model is then used to have a better starting point to learn new tasks faster, to adapt to these tasks faster. As we see on the right, this meta model allows us to adapt to task-specific architectures. In doing so, we do this in few-shot learning setting. So to introduce both of these components, Reptile and DARTS, the Meta-Learning and Neural Architecture search, we do so in the next slide. So Model-Agnostic Meta-Learning, or MAML, tries to find this better initialization for the parameters theta to adapt to new tasks faster. So as we see on the right, we combine a number of tasks, we adapt these during the inner loop, then we sum over these gradients and compute the second degree gradient to then find a better starting point for our model weights to adapt to our new tasks faster. The downside of this is that it usually requires the second degree gradient, which can be very expensive. That is why MetaNAS opted for a first order version Reptile. Secondly, the gradient-based neural architecture search, it applies a relaxation of the operations, which means that it introduces a alpha operator for every operation, which are then learned using a softmax distribution, applying bilevel optimization, in which we first adapt the model weights and then adapt the model architecture. In this bilevel fashion, we learn a good distribution on every edge of our cells, which then at the end we apply a discretization step to obtain our final model. This is, in a nutshell, differentiable architecture search. And to now introduce the problem statement of our work, we try to improve the generalizability of meta-learning of these neural architectures by regularization. So initially we wanted to improve the optimization gap, first introduced by Xie et al. In this paper from 2020, which divides the problems that gradient-based neural architecture search observes in these four categories, such as the gradient approximation errors with respect to alpha could be further improved so that we get better estimates. The joint optimization of the architecture and the weights introduce search instability, such as preferring weight-free operators like skip connections in early stages of training. The accuracy drops significantly after applying the discretization step because the network is not aware that this step will take place, and the retraining of networks might result in a worse performance because both pipelines might be different. So MetaNAS already employs two regularization techniques to try and deal with this gap. Initially, the soft pruning of the mixtures over operations and input nodes, which tries to deal with the retraining. This allows the network to know that discretization will take place and does not require the retraining. And then second, alpha thresholding, which removes small alpha from the final task-specific architecture to get a sparser network in the end. So to now the methods that we used, we used methods from progressive DARTS and SharpDARTS, and in these we observed the best performance increase. So we used methods from search-based regularization, namely limiting the skip connections. So limiting the number of skip connections in the normal cells to 2 is what PDARTS applied, and applying operation level dropout to the skip connections, which means we apply dropout after these skip connections to regularize the choices of these operations, and these all help us reduce the number of skip connections. Initially, as we see in the image, PDARTS uses a progressive search. However, in our small number of gradient steps, the progressive search does not lead to a better performance, actually worse. That's why we opted without this progressive search. And then for SharpDARTS, we applied alpha regularization and cosine annealing, which alpha regularization adjusts the weighing of the operation alphas during the forward loop, and the adjusted learning rate scheduler. These are all regularization techniques in which they observe a better performance as well. So what this then looked like is the following. Just using limiting and dropout on the skip connections, we improved the performance of MetaNAS by some percentage while maintaining relatively the same number of parameters. And then further, also adding the regularization of SharpDARTS, we greatly reduce the number of parameters, mostly owed to the alpha regularization, and also reducing this number of model parameters. So what is interesting is that we reduce the number of model parameters significantly, especially compared to just MetaNAS, which could maybe indicate that we're choosing more task-specific architectures. And then our second adjustment is using TSE-DARTS, which basically is optimization without a validation set. So bi-level optimization assumes the availability of a validation set during the optimization of the architecture, and then during the inner loop we adjust the model parameters. However, in few-shot learning there is no access to a validation set. We only have access to the training set, so we'll use the training set in both cases, and this is what TSE-DARTS accounts for. It introduces this generalization estimator to account for this setting, and instead optimizes a different objective, namely the marginal likelihood for the alphas, resulting in this different gradient which we will have to replace. So in doing so, we observe the following results. Just applying TSE-DARTS gives us a huge performance increase, the biggest we've seen on OmniGlot one-shot 20-way. And then on the other setting as well, however, there's a large model parameter difference. So what we can see is also applying the other regularization methods, we do not yet see a better performance. However, further parameter tuning, hyperparameter tuning could lead to having this better performance in the future. So to conclude, we presented a number of regularization methods such as limiting and dropout on the skip connections, max W regularization, and the adjusted learning rate scheduler, which improve over MetaNAS. Moreover, accounting for this optimization setting without a validation set also greatly improve the performance of MetaNAS and are interesting. So for our future work, we would like to further improve the generalization ability of MetaNAS. We hypothesize that adjusting the meta learner to a meta reinforcement learner might lead to more task-specific architectures. As we see on the right, now we would have an agent optimizing the task architecture, which might be interesting to look at in the future. If you have any questions, please feel free to reach out during the poster sessions.